What is up, guys? How we doing? This is Mr. Martinez back with another video for our mini series. Today we're studying Newton's laws of motion. So let's just jump right into it. First law, an object at rest remains at rest. Okay, so this is the law of inertia. Okay. And an object in motion remains in motion. Here's the key, at a constant speed and in a straight line. Okay, so all the examples, we'll use the color orange for that. All those examples mean that the net force is 0 newtons. All of the arrows, all the vectors balance out, and that means that they're constant. Okay, let's look at the rest of this. Unless acted upon by an unbalanced force. Well, what that means is that the net force would not be 0. Okay, that means that when you add up all the vectors, it's going to be any number or any value other than 0. That's the only way to change an object in motion, in constant speed in a straight line, or an object at rest, remaining at rest. You have to do this, which is apply an unbalanced force. Okay, second law, let's look at that one. So the second law says that's, for those that don't remember, F equals ma. Okay, the acceleration of an object depends on the mass of the object and the amount of force. So FMA. Moving on, let's go ahead and use yellow. So the third law is, in my opinion, the easiest. Whenever one object exerts a force on another object, the second object exerts an equal and opposite on the first. What does that mean? We call that action reaction. Okay, and I'm not going to write it all out, but you get the idea. All right, so let's get started with some examples. All right, let's go ahead and turn our attention to the first law of motion, which is inertia. And as we can see here, the box is at rest. Therefore, the net force is 0 newtons. That means that the arrows or the vectors that are applied to the box balance out and it equals 0. So if it's at rest, it's going to stay at rest. And don't forget, guys, just because something is at rest doesn't mean there are no forces acting on it. There are always, this is how they trick you, forces acting all the time, even on things in space. So don't get tricked by that. Even though the net force is 0, there's always forces acting. They're just balanced. So here, this guy is going to apply an unbalanced force, and that's going to cause this box to accelerate. Okay, and then if he can apply a consistent force, then you can have constant speed and the same direction until, of course, another unbalanced force hits, like maybe he pushes it and it bumps into a wall, or he falls off a cliff, whatever. Okay, so we're only looking at the first law. Let's go ahead and get some practice questions, and then we'll move on to the second law. Okay, let's look at an example or two just to make sure that this is making a connection with y'all. So this first one here, we have 3 eggs here at the top. They have inertia, so they want to stay at rest. However, an unbalanced force moves this tray, and then the unbalanced force of gravity will push them down in a straight line into their cups. Okay, and that's because they have inertia. What's at rest wants to stay at rest, and once they're accelerating downwards because of the unbalanced force of gravity, they go in a straight line and they fall into the cups. Okay, let's look at a second example here. So we have a car. Let's pretend the car is going 85 miles per hour. That means everything in the vehicle is also traveling at that speed as well. Okay, you could see that none of these crash dummies on the left side, which are these two guys right here, they're not wearing their seatbelts, so they want to keep traveling forward at 85 miles an hour. Why? Because they have inertia. Okay, if you look at the other two in the back, they have their seatbelts. The seatbelts will put a force greater than what's going forward onto them to overcome their inertia. So if they are 100 Newton dummies, then the seatbelts will have to put greater than 100. Let's just say they have to put 150 newtons, and that is an unbalanced force that will stop and change their motion. Otherwise, you end up like the guys on the left side of the car that keep going forward until they hit an unbalanced force of the windshield or the front seat right there. Okay, So hopefully that makes sense to y'all. Let's continue on. All right, let's try a practice question here. A steel ball is at one end of the box moving forward. The box suddenly stops. You can see that it's moving forward here. According to Newton's first law, and that is going to be the law of inertia, so we'll keep that I there. What happens to the steel ball just after the box stops? Okay, so first thing we want to remember is what's the first law? An object in motion stays in motion in a straight line at a constant speed. So if you know that, we can answer this really easy without even looking at the picture. So because of friction, well, that's not Newton's first law. Because of friction, that's not Newton's first law. So if you want to pause the video here and try to see which one you guys come up with, go ahead and do that right now. Okay, welcome back. Because of inertia, which that's what we want, that's the first law, the ball continues to roll forward at the same speed. Well, that's kind of what we described, right? But let's look at the other one to just make sure. Because of inertia, that's also correct, the ball rolls forward at an increasing speed. So the rule says straight line, constant speed. So what is constant? Is it forward at the same speed or increased speed? If you guessed same speed, then you're right. The answer is H. Let's try another. Okay, so this one says a large rock is motionless on a flat sidewalk. Which statement best explains why the rock remains motionless? So another way we can describe motionless would be at rest. Okay? What do we learn about at rest? I told you it's 0 newtons if it's at rest. If it's 0 newtons, that means the forces are balanced. So let's see which one says that. If you want to try this on your own, pause the video right now. Okay, hopefully you got your answer. Let's see. So there are no forces acting on the rock. Well, if you didn't pay attention, you're probably going to pick that one. But if you did pay attention, you were taught correctly, and that is wrong because there are always forces acting on everything. There's never an instance in the universe, in life, when things are not being acted upon by forces. So get that out of your head right now. Gee, the only force acting on the rock was directed toward the sidewalk? No, forces come in pairs. They don't come one at a time. Forces acting on the rock are balanced. Okay, that's what we talked about. And then the sidewalk exerts an unbalanced force on the rock. If it did, then the rock would move because it wouldn't be 0 newtons. It would be anything but 0, causing it to accelerate. So the correct answer is H. Okay, now let's go ahead and finish the first law. We're going to focus on the second law, and that is going to be our triangle. So F, M, A, and we'll do a better drawing of it in the other one, okay? Here we go. In case you forgot what it looks like, I'm going to go ahead and show you. So let's look at the two forces here. They are the same size, and they're the same direction. So the forces are the same. So let's just say that the force is 100. We'll just quantify it, give it a number. So if someone is pulling the wagon with 100 newtons, if this has a greater mass, like that looks like a lot heavier than the one on the bottom, then that means you're going to have very little acceleration. If you have a smaller mass, that means that the acceleration is going to be much greater. Why? Because there's less resistance. So there you go. That's Newton's second law, in case you forgot it. If the force is the same and the mass is more, you have less acceleration. If the mass is less and you're pulling exactly the same, which is 100 and 100, you're going to have it accelerate a whole lot more. And that's just kind of like common sense. And then here's what it looks like in action. So you have person A with a little bit of mass, and you have person B with a lot of mass. You push them the same, and they react differently. Okay, let's try some practice questions. Okay, so here's our first question. A student uses a magnet to move a 0.025 kilogram metal ball. So that is going to be our mass. When you guys get this on the test, put an M over that number. That way you know that that is your mass because it has kilograms or grams. That's going to be mass. The magnet exerts a force. We know force is measured in newtons. So we're going to put F here on top, which causes the ball to begin to move. Okay, what is the acceleration? So we are looking for A. Okay, that's how you guys are going to break this down. I want you to use the strategy. Put the F, the M, and the A where they go in the question. Okay, so all we have to do is we're looking for A. That means we're covering up A. And if we cover up A, what does it tell us to do? It tells us F divided by M. So that would be 5 divided by 0.025. And you always put the top in the box when you divide, or the top goes in the calculator first. So 5 divided by 0.025. Guys, why don't you go ahead and do that and see if your answer's on the question. Go ahead and do that right now. Okay, so if you ended up with 200, then you got the right answer because the top always goes in the calculator first. Now, one thing to remember that we haven't talked about, meters per second squared, m/s with the little 2 on top, that is always how you measure acceleration. So that never changes. So if they ever ask you a question, which one's an example of acceleration, it has to have that unit. That never changes. Moving on. Okay. A 1,100 kilogram car, so that's going to be mass, comes uniformly to a stop if a vehicle is accelerating at negative 1.2 meters per second. Remember we said this gives it away. That's going to be A for acceleration. Which force, okay, so we're looking for F, force, is closest to the net force acting on the vehicle. So we're going to cover F, and our triangle tells us to do what? M times A. Go ahead and try it. Pause the video right now. Okay, coming back, what did you guys get? You should have got 1,100 multiplied by 1.2, and your answer should have been, and it wants to say the closest, so you're not looking for the exact answer, you're looking for the thing that is the closest to what you came up with, which should have been negative 1,300. If you guys wanted a precise answer, it would have been 1,320 newtons, that negative. That would have been your answer. But the closest one is G. Okay, we're done with those first two. Our last one is Newton's third law, and that is action reaction. Let's do it. Okay, so your mother and daughter press their hands together and push apart. So they both are pushing with the same force, equal and opposite. The daughter's going to go this way, the mother's going to go this way. Well, how come I didn't draw the arrows the same size? Well, the daughter only has a mass of 50 kilograms and the mother has a mass that's double that. So that's why you can see the discrepancy in the sizes. It's like the bullet and the gun. Why doesn't the gun fly as far as the bullet? Well, it has a lot more mass, has a lot more inertia, and you're holding it. The bullet, on the other hand, has less mass, less inertia, so you can fly really fast forward and have a great acceleration. So immediately after they push away from each other, how does the motion of the mother and daughter change? So the mother moves forward. Is the mom going to move forward? Well, we drew her arrow going backwards, so that's wrong. Both of them move forward. So are they both going to move forward? Well, we drew they're both moving backwards, so that would be wrong. So the mother moves backwards and the daughter moves forward. Okay, well, we looked at our vectors and that's not what it shows. J says both move backward, but the daughter moves with a greater acceleration. So this would be the one that we diagrammed. So J would be our answer. They're both going to move backwards. And as we have the bigger vector right here, she's going to accelerate more because she has less mass. All right, a photographed bird is perched up on a fence below. Okay, which description identifies action-reaction? So we know that that's the third law, okay, between the bird and the post. Well, one of the rules, and this is why we did this example of the high fives in the classroom, one of the rules for action reaction is it's the point of contact. Where do the two things touch? So when we did high fives and we're abusing each other, okay, we felt pain in the hands, not in our arm, not in our stomach, not in our feet. It was where they touched. So where is the bird touching the post? Because that's what it wants to know. The bird and the post. Well, it's touching right here. And when it's doing that, the net force is 0, meaning that the bird is not accelerating. It's just at rest. It's just hanging out. So that means that the forces have to be equal, opposite, and balanced. So let's see, the action is the force of the bird on the wires, and the reaction is the force of the wires on the fence post. That's not what we circled, so no. G, the force of the wires on the fence post, and then the reaction is the force of the fence post on the bird. We're not touching the wires, so I don't know why I keep saying wires. We're not touching the wires, so that's wrong. H, the force of the fence post on the bird, and the reaction is the force of the bird on the wires. Okay, again, we're talking wires. That's not necessarily what we're looking for. And then our last one, action. The force of the bird on the fence post. Okay, so bird on the fence post. The reaction is the force of the fence post on the bird. Well, there we go. Now we're not touching these wires. We're touching the post right here. That's why we circle that. That's the point of contact. The only answer that makes any sense has to be J. Okay, guys, that's going to do it for this mini video. Get in Canvas and work on your do first, do second, and do third for Newton's laws. We'll catch you in the next one. See you guys.